Because not everyone was here Friday, I'm not passing back the quiz yet. But the number one mistake I saw on the quiz was one when you're doing variables. When it asks you to give your variables, don't just put random numbers. That means nothing to me. I'll put kilogram, degree Celsius. Again, means nothing. You need to put mass equals this, PI equals that, PF equals that. You need to include the variable and the value, like we've been doing all year long in the entire example. Also, when doing the equation, so when it asks you to provide the equation, don't just put M delta T CP. You should be putting also the Q, the full equation. So if you got the entire problem wrong, and you did this and this fully, I gave partial credit. The number one mistake I saw was something like this. So the question said, how much heat is released when 50 kilograms of water goes from 10 degrees Celsius to 20 degrees Celsius. So someone would come over here and write Q equals M delta T CP. Actually, they wouldn't write the equation, but I tell you, you need to start with the equation. And Michael and everyone putting on his mask. So the number one mistake is they just take all the numbers and plug them in directly. 50 times 10 times 20. Again, that's incorrect. What mass, so if I were to actually write this, mass is 50 kilograms. TI is 10 degrees Celsius. TF is equal to 20 degrees Celsius. This is supposed to be CP. Why are you plugging this number into CP? Why are you plugging 10 into delta T? Y'all just multiplied all three numbers together without actually figuring out what does CP represent. What is delta T? Delta T is final minus initial. It was written on your equation sheet. Anyway, today we're continuing on. Let me find the PowerPoint. No! We're doing something else. You mind closing the door, Uncle? Let me make sure this is the correct. And let me look at the test. Make sure that where it's not. Alright. So we're going to look at ways heat transfers. how does energy move from one object to another? So how does heat flow from a fire into something else? Does anyone know? So it but how does that heat get transferred? So let's say you're standing next to a fire. How is it primarily heating you up? So again, how is that heat moving? What is heat? Heat is energy. Do we directly say energy? So what is temperature? I keep repeating, I'm saying this every single day almost. What is the definition of temperature? The average, the average kinetic energy. How fast on average are the molecules moving? So how does fire make the molecules in your body start jiggling faster and moving around faster? So reviewing heat, heat or thermal energy is created by the movement of particles. So heat energy is the total energy of a substance. And y'all quit talking. It's a measure of the movement of the particles and also their configuration. Heat increases as temperature increases because as temperature increases, atoms move faster. They have more kinetic energy. So good? So heat or thermal energy is transferred from one object to another when objects are at different temperatures. The amount of heat that is transferred from two objects, the amount of heat that is transferred when two objects are brought into contact depends on the difference in temperature between the objects. So how much heat is actually transferred depends on the temperature difference. Y'all finished? Heat is transferred only when two objects are at different temperatures. Thermal energy always moves from warmer to cooler objects. The warmer object loses thermal energy and becomes cooler, while the cooler object gains thermal energy and becomes warmer. Energy will continue to move from a warmer object to a cooler object until both have the same temperature. The main thing to get away from this is heat always goes from warm to cold, or it goes from hot to cold. So heat always moves in the direction of hot to cold, and it'll continue moving until they reach the same temperature. Michael, put your mask on. So what happens to the coffee as it continues to sit? Where does the heat go? It goes into the table, it goes into the air, anything that's in contact with the coffee. It goes into the mug, which then goes into the table. So, because, yes, that's correct. And it'll continue until eventually they reach some steady temperature. So it'll flow away from the coffee, and everything else will warm up around it. The desk would actually get hotter, but because the desk has more mass, you probably won't notice a differences in temperature. Yeah, but eventually that heat will spread out over a long period of time. So there are three main ways that heat can transfer: by conduction, convection, and radiation. So heat can transfer in only three main ways: conduction, convection, and radiation. You'll need to memorize what each three of them means, as that's what a good portion of the tests will be asking about this, I believe. A significant portion, at least. So, let's look at conduction first. Conduction is the transfer of heat by direct contact. This is when the particles are physically touching, and the vibrations of neighboring particles move and start vibrating the other. So conduction occurs most easily in solids and liquids. So for example, if you put a skillet over a fire, the heat will travel up the handle because all the molecules in the handle are next to each other. Because all the molecules in the handle are really close, if the molecules closer to the flame start vibrating faster, they're going to bump into their neighbors. As they continue to bump into their neighbors, it's going to spread until it reaches the rest of the handle. So this is probably what y'all are thinking at the very beginning. Conduction is whenever things are directly touching. So the fire is going to heat up the air. Those air molecules are going to bounce and hit the bottom surface of the skillet, and they're going to cause the skillet at the very bottom of it to start vibrating faster and faster. They're going to run and hit into their neighbors, which are going to cause them to vibrate faster and faster. So why is it easier in solids and liquids than it is in gases? So in gases, they are very far apart. So atoms and molecules are closer together in solids and liquids. So the particles need to only move a short distance before they bump into another. This is a very good animation of conduction. If we look at the very left when it starts, we can see that only the left atoms start moving. But as they start moving, they start bouncing into their neighbors, causing them to start vibrating. And it very slowly goes and transfers along the material. You also have to remember that atoms are very, very tiny. And so it doesn't, and on a macroscopic scale, on the scale that we are used to, this would actually occur very fast. But it does this animation where only the atoms on the very left is actually absorbing the heat. They're getting hotter and hotter, but because they're next to other atoms, they're going to transfer some of their heat to their neighbors. And this is going to propagate down until all of them reach the same temperature. Again, this is conduction. So the direction of heat is going into the first column of atoms, and then they're bouncing left to right. The heat is flowing to the right, to the colder. So heat is flowing from hot to cold. So explain the movement of thermal energy in this picture. It would be from your hand to the ice. So the atoms that make up the cells on the surface of your skin. So you have to think about this on the atomic level, smaller than a single cell. The atoms are vibrating, and whenever the ice touches your hand, some of that vibrational energy is bumped into the ice, causing the ice to warm up. So it's going. So the ice is only making your hand cold. And Thomas and John, lift y'all's heads up and keep y'all's eyes open. So it's not so much as the ice is making your hand cold. It's more like your hand is giving up some of its heat to warm up the ice. Yes, by giving away its heat to warm up the ice. So faster moving molecules in your warm hand bump into the slower moving molecules in the ice. The thermal energy moves from your warmer hand to the colder ice. The slower moving molecules in the ice move faster. So how is this an example of conduction? Yes. This is an example of conduction because the faster moving molecules in your warm hand bump against slower moving molecules. Yes. It doesn't cause super burn. It can cause a freezer burn, which isn't really a burn. It's frostbite. Keeping your hand on ice can cause frostbite by itself. But anyway, slower moving molecules in the ice. You don't really need salt, by the way. You can do that with just normal ice. Just salt lowers the melting point temperature, so the ice gets colder. Direct contact. So this is because of direct contact with particles where they're bumping into each other to transfer heat. So, if you were to wave noodles above some hot container, the steam coming off, how is the movement of thermal energy if you were let's say you remove some hot noodles, how would you explain the thermal energy as it cools off while sitting there in the air? So, when air molecules collide with the molecules inside the noodle, because it's hotter than normal air, it's going to transfer and bounce the air molecules back faster. It's going to make the air molecules that are hitting the noodle bounce away at faster speed. So the air molecules are going to the noodle is going to give some of its energy, heat energy, to the surrounding air. So how does the lady in pink drop her roasted stick before the lady in the green dress? Yeah, so it's shorter. You can say it's because it's shorter, it can quickly spread across of it. Yeah. Yes, it would. So metal gets hotter way faster than wood, and so there are two types of materials, which is exactly what we're talking about: conductors and insulators. Substances that transfer thermal energy very well are called conductors, like metal. So a metal conducts thermal energy very well. So if you take a metal poker, put it in a fire, it's going to conduct the heat energy very fast. Substances that do not transfer thermal energy very well are called insulators. Yes, there's electrical and there's thermal. So there's thermal conductors and there's electrical conductors. There's also thermal insulators and electrical insulators. Yes. So there are some things that can conduct energy or electricity very well, but can't conduct heat very well. Carbon, like your pencil lead, can conduct electricity very well, but can't conduct heat as fast as metal can. So some examples of good conductors, this is again referring to thermal conductors or heat conductors: silver, copper, gold, aluminum, magnesium, tungsten, nickel, mercury, platinum, iron. Some decent conductors, they don't perform as well as the good conductors: graphite, which is your pencil lead, the human body, damp skin, salt water, earth, silicon. These don't really conduct heat very well. Good insulators would include oil, wool, silk, rubber, plastic, wood, paper. By the way, why does putting on a blanket keep you warm? No, it doesn't matter the material. Why does putting on layers of clothing keep you warm? So, so our body is constantly generating heat. And as air molecules come and hit our skin, they steal some of the heat from our bodies. Wool, or silk, or cotton, or clothing and blankets are all made out of a material that doesn't really that prevents heat from going through it really quickly. So while we're generating heat, it's not that the blanket's making it warm, it's just preventing the heat from escaping into the air. So it keeps the heat trapped in around your body. So the next one is convection. You might have heard of a convection oven. A convection is the flow of currents in a liquid or gas, or a fluid. So fluid includes both liquids and gases. We'll see once we go over it a little bit. So in a convection transfer of heat, a current is created when warmer or less dense material rises, forcing cooler air to sink. So you have these loops. So whenever you heat, so things that are heated by convection occurs whenever something hot is getting, or something is getting hotter and causes the rise to the surface. And this causes, because it's rising to the surface, this causes the cooler material to fall down and get heated up. So you can see that as the water gets hotter, it becomes less dense and rises to the surface. And as the water near the surface becomes cooler, it sinks down to the bottom next to the fire. So in this system, we see conduction going on between the flame and the bottom of the pot, and from the bottom of the pot to the bottom layer of water. So that's conduction. However, most of all the water is heated by convection, this rising and falling of water. The warm water being heated and rising to the top, and the cooler water sinking down to the bottom. So this motion of a hotter rising and cooler sinking is convection. So let's look at some examples. So we have ocean currents. Ocean currents are caused by convection. So let's say you had a radiator in your room. It heats up air around it, and the air will rise to the top. Because as it warms, it becomes less dense and rises to the ceiling. This means that the air that's colder, that's farther away from the radiator, is going to be pulled down below, and then move in the direction of the radiator. So in convection example like this, most of the warm heat is going to be above the radiator. And lift your head up, Michael, and put your mask on properly. So in convection, most of the heat goes upward and not outward. So this generally radiators like this is used to heat up the entire room, and it's the reason why we don't get super hot when we're next to them, and the room stays at relatively constant temperature, because most of the super hot air is going to rise up above the radiator and be closer to the ceiling. We also see, like when we're boiling water, we get the circular motion. Well, as the sun heats up the road, the hot air will rise up and the cold air will fall down below it until we get to the surface. When a candle heats up, most of the heat is going to go directly upward. It's going to spread out, pushing cooler air downward that will continue in a cycle. The last one is radiation. Radiation is the heat transferred through space by electromagnetic waves. Electromagnetic waves is light. That light might not be visible. It could be infrared, it could be ultraviolet or UV light. By the way, did y'all know that everything in the universe glows? That you're currently glowing? What what color are you glowing at? See? You're close. So if you were to stand in a completely dark room with no visible light, you would glow. Can y'all think of any? And put your mask on. Can y'all think of any certain type of goggles that allow you to see in the dark? How does night vision work? Heat sensors. What heat or wavelength of light do they see? Infrared. So we're currently giving off infrared light. So this is because our atoms have electrons that are moving around. So as electrons move, they produce electromagnetic waves that give off light. So unlike conduction and convection, radiation can occur in empty spaces as well as in solid, liquids, and gases. So radiation can go through the vacuum of space. It also goes the easiest through gases or air. Waves such as visible light, infrared, and ultraviolet lights are examples of this electromagnetic radiation. So, has any of y'all ever parked in the winter partially under a tree and noticed the portion of your vehicle that's under the tree has frost over the window, and the portion that's not under the tree is, or the portion that was under the tree doesn't have any frost on it, but the portion that was not under the tree and up in air has frost over it? Why is that? The tree is glowing in infrared. And the closer you are under that tree, the tree is giving off heat via infrared radiation. So, yes. So, fireplaces. When I asked this at the very beginning, fire actually. So, if you're at a bonfire, almost all the heat is. So, how is it going to work? There's conduction. The air molecules next to it are going to be warmed up as they touch the flame. They don't really vibrate too well, so conduction doesn't work too well through gases. So conduction isn't going to heat you up. It's not going to be able to bounce into neighboring gas molecules because gases don't really work in conduction. However, there is convection, but convection is going to cause all the heat to rise up into the air, or in a chimney, up in the air, if you're doing inside your house. So almost all the heat is not going to radiate outward to everyone else near it. The reason why fire actually heats you up is all due to the light it gives off. Almost all the light, and Thomas, put your mask on properly. Almost all of the heat you feel is directly due to the light it produces. And next time you stand next to a fire, think about it. If it's heating up all the air around you, if you stand next to a fire, shouldn't the air just flow past you and you should feel heat on your back and your front? And if the air was heating up, if the air was actually heating up, you'd feel the warm air go around you and heat both sides of your body. But when you're standing next to a fire, you only feel hot that is actually have light shining on it, right? So the primary way the sun heats up the earth is due to electromagnetic waves or radiation. You might have seen at gas stations and buffets, you have these special lamps. The lamps actually produce a lot of infrared. They're called heat lamps. So they're heating up the food by just shining light on it. It's actually producing a lot of infrared radiation. And microwaves. Microwaves are the form of electromagnetic light. So a microwave is a type of light, we can't see it. Just like infrared is a type of light, we can't see infrared. But that can be absorbed in your food and cause it to warm up. Yes. They'll start, some parts of them will start falling, and then the gases inside of them will start expanding. It'd be a very unpleasant way to die. They'll mess up the electrical neurons. It'd be painful. So look at this image. This image shows all three types of heat going on. We got the fire primarily heating everything by radiation. We got the water inside of it heating by convection, which causes the top of the metal to start heating up by conduction. So the entire handle heats up by conduction. The water is going to heat up by convection, and the fire is going to heat up the pot primarily through radiation. Yo, just get strong. So here's another example. So the person up above is going to get a lot of the heat by convection. So the air molecules next to the flame are going to heat up and are going to go straight upward due to being less dense. So convection, that's the reason why if you put your hand over a fire or a candle, your hand's going to get really, really hot and probably burn. However, if you put it to the side of the candle, almost all the heat energy is going to be mostly through radiation. And if you put a spoon into the fire, you're going to feel the spoon get super hot, and that's going to be due to conduction. So look at the three images below. Identify which one is conduction, convection, and radiation. Yes. So the very first one, so the fire is going up into the heat by convection is going up into that little pipe, and he's not directly touching the fire, so it has to be radiation. The light given off by the flames is warming them up. And B, he's taking a pole and putting it directly into the fire. This is causing it to spread through the pole by conduction. And in part C, he's blowing cold air or warm air down, which is called doing cold air downward, which causes it to rotate. The hot air will go upward or do something, or in reverse, depending. It looks like he has it on winter settings. Blades are done closer, so the colder air will go down, forcing the warmer air to go upward. Just three different images. Alright, so what is number one? Conduction. What is number two? Convection. And what is number three? Radiation. So, again, I tell y'all that everything around room temperature is glowing at infrared. As you heat it up, it'll eventually transition into the visible spectrum. If you have an electric oven and it has a bar that starts glowing red, and then orange, and then white, you can see as it looks black usually, and then you start seeing it very faintly turn red. As you heat it up, the color it's glowing at is going to gradually shift to become more visible. So it'll slowly become a dark red, then a very bright red, then an orange, then yellow, and then if you get it white hot, it'll turn white. If you get it hotter than white, it'll eventually turn a pale blue, and then eventually blue, and then if you get it super hot, it'll turn into ultraviolet. You can't reach ultraviolet. You need to be as hot as the sun. So in order to get blue flames are super hot. To go beyond blue, you have to really get into like a sun. That's also due to something else. That's also you breaking the chemical bonds and causing it to release a specific color. That's the reason why you have multicolored fireworks. It's not directly based on temperature, it's based on what atoms are being broken down to. So that's it for today. And here's the code word.